Okay, so soon we're going to move on to the other major Earth system process, and that's atmospheric processes. But before we do, we should look at one of the components that links, let's say, the lithospheric parts and processes that we have been looking at with the atmospheric processes, and we can call that the hydrological cycle. Now, I'm sure many of you have heard of and even studied the hydrological cycle, especially if you did any geography or science at school. And there's plenty of basic videos and pictures and tutorials online that can explain that. So we'll just go quickly through a description of what the water cycle is, and then look at those components in a bit more detail to helpfully increase your understanding. So this is the hydrological cycle. Now, because it's a cycle, you can start anywhere in that cycle and explore it. But we'll just start with precipitation. Everybody knows what that is. It's rain mainly, or snow, or hail. And it's the movement of water from its gaseous form into its liquid form that then falls towards the Earth from the atmosphere. Now, that precipitation then hits the Earth's surface and can do one of two things. It can collect on the Earth's surface and run off in rivers and streams. The other thing it can do is infiltrate through the soil, and if it does that, it can then move down into what we term the groundwater, and then either as it moves via runoff or moves through groundwater, it will then eventually return to the ocean. Once it's back in the ocean, the sun can take over. Now, the sun is the driver of the hydrological cycle. It converts the liquid water back into water vapor, which then can fall back down as rainfall, thus completing the cycle. All right, so that's the hydrological cycle. And look, we've looked at parts of the hydrological cycle, seen how it influences some of the processes that have occurred in the more lithospheric parts of it. So particularly when we looked at sedimentary rocks, and we talked about weathering, which was influenced a lot by water, and certainly transportation of those sediments by water, and then deposition in water that then precedes the formation of sedimentary rocks. So we've sort of seen how it is involved in many other processes. So the hydrological cycle links not only the lithospheric part and the atmospheric part, but also drives the biosphere, of course. Plants and animals and us are dependent upon it. And so it sort of links all of those spheres, the biosphere, the hydrosphere, the lithosphere, and the atmosphere. We can all have a part in the hydrological cycle. Okay, so let's have a look at each of those components in a bit more detail. So the first one we started with was precipitation. Well, as you probably know, precipitation varies greatly across the Earth. Very high in places like the tropics, and we'll see why it's higher in tropics and lower in other parts a bit later on. If we look at Australia's rainfall, similarly, we can see that it's distributed widely and it differs depending on where you are, concentrated in the tropical regions, but also in the coastal regions, and much, much drier in our arid centre. But the distribution of rainfall is not the only interesting thing. You can also look at the variability. Rainfall doesn't fall the same every year. Averages are really very rare. And as we know, Australia is a land of drought and flooding rains, and that really reflects its variability. And you can look at maps of variability, this one produced from the Bureau of Meteorology, and you can see there that, again, not unsurprisingly, the more variable parts of the continent in relation to rainfall are in those much more arid areas where it does rain occasionally, and when it does rain, you can get very large amounts of rainfall occurring as storms, and then other years, you can get next to nothing. Now that's an indication of how variable it is. Whereas it's less variable in other parts, particularly in the more temperate and more coastal regions. You can have a look at a global map of variability, and you can see that there are other parts of the world that are similarly and even slightly more variable, particularly in the arid parts of Africa. But you know, a significant part of Australia is represented there as highly variable in its rainfall. And we know that. We know we face droughts very commonly, particularly in the last 20 to 30 to 40 years. And that the occurrence of droughts is a reflection of the variability that we can measure in relation to rainfall. Rainfall falls and then, as I said, can do one of two things. It either can collect on the surface or infiltrate. Now, if we have a look at it as in its collecting form, it will form puddles, and then those puddles will grow larger and start to run off downslope into streams and rivers. Now, similarly, the amount of runoff varies greatly, varies widely globally, and will, of course, be related to the amount of rainfall that is occurring in those same locations. And we can have a look at the runoff in Australia, and you can see that map there. We have a fairly large river system. In fact, it's the same length as some of the major, or similar lengths as some of the major river systems like the Amazon. And if we have a look at this diagram here, this is the amount of discharge, or the amount of water that goes down the Murray River, our largest river, every second. And it's 400,000 litres of water every second on average. That's a lot of water, 400,000 litres every second as you go past. Now, if we just put on there, on next to it, the same, the discharge of, let's say, similarly length, a river of about a similar length, the Amazon, and see what its discharge is, you can see that it's appears to have gone off the scale. Let's change the scale from 1,000 litres per second to million litres per second. Let's put the Amazon on, and let's put our Piddling Little Murray on. And you can see there the relationship between our major river and, admittedly, the largest river on the planet. But it nonetheless reflects how dry our continent is. So it's not only, so we know it's dry because we know about the deserts. We had a look at its variability in rainfall, and that's reflected in the amount of runoff that occurs. Our rivers are very, very small, globally speaking. And you can see in this graph here a comparison of the discharge of some of the major river systems and our little one at the bottom there. All right, so now one of the things that can happen in between the rainfall that comes out of the clouds and it collecting on the surface, and it's not often looked at, and I didn't talk about it in that quick introduction, it's interception. Now, you think, well, what does that mean? As rain falls, it gets collected on trees. Well, eventually that just drops off and goes onto the ground, and then can either infiltrate or form runoff. Well, it's not actually true. Depending on where you are, and of course it depends on the vegetation of your location, interception, which is the rainfall that is stopped by the vegetation, can be significant. And studies have shown that in forest areas, it can be as high as 60% of that precipitation is stopped and stored on the vegetation, depending on the intensity of the rainstorm. But on average, it can be that high.
Now, while a significant amount of that will be lost as evaporation,
an adaptation of vegetation so that it actually collects the rainfall and either then channels it down through the stem, we call that stem flow, so that it is then concentrated near the roots of that particular tree, or other trees collected on the leaves and then drip it at the drip line of the tree, and similarly is aimed at increasing the amount of moisture that is available to those trees' root systems. So interception can be a significant part of the hydrological cycle, and you can see how where it can be important for particular systems. Okay, so if that rainfall does make it to the ground surface. It can infiltrate, it can collect as surface water and run off, which we've looked at, or it can infiltrate. Now, infiltration is just the movement of water into the soil. Now, you can measure infiltration. Now, this little system here, if you do the subject in soils with me later on, then you'll get to do this at home. We send you a little kit and there's a little infiltration ring. And it's a very simple process. You drive that ring a little bit into the ground and then you pour some water into it, put a ruler inside the steel ring, and you measure the rate of the fall of water. Now that's useful in a comparative mode, so you can compare particular areas. Perhaps you're, let's say, interested in agriculture. You can compare different paddocks or fields that you want to perhaps want to grow something, and you want to make sure that water can actually get into the soil. And so if you have a paddock where you measure it and the infiltration rate is very, very slow, you might think, well, that could be problematic down the track if the moisture is not getting into the soil. If it goes in too quickly, well, perhaps that's an indication that water storage might be a problem. Anyway, you learn about that if you do my subject later on. What we can see is that infiltration is different. The infiltration rate changes depending on the particle size. And this little animation here just shows you different particle sizes, as we looked at before, will affect how fast water can infiltrate. And that makes sense too, because the smaller particles, remember those flat clay particles, well, they don't create many pore spaces. With the big beach balls, no fancy beach ball this time, the big beach balls produce much larger spaces in between them because they don't fit together like flat clay particles. And so there's less pore space for the water to move through, so it moves through slower. It makes sense. You can do a thought experiment, get a bucket of sand and a bucket of clay, pour water into each of those. You know which one's going to move more quickly. Okay, that's infiltration. And you can, if you know the infiltration rate and the rainfall rate, you can predict whether or not you're going to get runoff. If your rainfall rate in a particular rainstorm is higher than your infiltration rate, then water won't be able to move into the soil at the same rate and will start to pool and will cause runoff. And that can be important if you're trying to understand erosion, because as water moves across the surface, it will cause erosion of particles, like what we saw before when we looked at transportation and sedimentary rocks. But if the water does move all the way into the soil and continues to move down, it can move into what's known as the groundwater. And this is a cross-section of a landscape showing you groundwater. Now, in the landscape, you will have what's known as the water table. Now, the water table, it's an often misunderstood term, is simply the line separating the area of unsaturated sediments in soil and that of the saturated sediment in soil. So groundwater is beneath the water table. Now, unfortunately, one of the other major misconceptions, or perhaps the major misconception, is that groundwater is water that collects in caves and is stored in these big caverns underneath the ground. And this diagram here sort of perpetuates that misconception. I did a search for groundwater, and on an educational site, a school site, this diagram came up, and I thought, oh, it's not quite right. Sure, water does collect in underground caverns, and limestone caves are a good example of where that occurs, but it's not where most of the groundwater on the planet, or not how it occurs, or it's not how it appears in the it's not how it appears beneath the surface. Groundwater is mainly stored in those little pore spaces between the particles of sediment beneath the surface. And so it just fills up those pore spaces. And when it's in those pore spaces, it can move. And the position of that water table can move up and down. It'll move up if rainfall falls and infiltrates and makes it all the way to the water table, and we call that recharge. Now, it can move up and down depending on the season, And so this diagram here shows you a high water table. Now, if your high water table, or if your high rainfall occurs in winter, then your water table will rise. And then if your dry rainfall season is in summer, your water table will fall. Now, the reason this diagram is interesting is that it also shows the relationship between the water table and the landscape. And if the water table intersects the landscape, then you can get a river. Now, not all rivers form in this way. You can just get rivers forming from runoff. And in fact, the opposite happens where water moves out of the rivers. We call that a losing stream. If the water table intersects with the landscape and water is moving into that river system, we call that a gaining stream. The other feature that you can see where the water table intercepts with the landscape is in springs. If you're walking up a hill and suddenly there's this wet area coming out of the side of the hill, you call that a spring. Well, that's because the water table itself has intersected with the landscape. Now, water in the water table, or groundwater, can move, and it'll move due to gravity, just like water will anywhere. Now, the rate that it moves will, like we saw before, similar to infiltration, will depend on the particle sizes, because the larger particle sizes will give us more pore spaces. And so measurements have been done to show the velocity of groundwater moving, and it ranges from relatively fast in sandy or pebbly, gravelly sediments to extremely slow in rocks, although in rocks like sandstones you do get water movement. There's enough pore spaces in the sandstone, even though it's compressed and cemented together, sandstones still transmit water. And you can see that because if you get a sandstone, a dry sandstone, and you weigh it, record the weight, and then you take that sandstone and put it in a bucket of water and leave it for several days or weeks. And then after a while, take it out of the bucket, dry it off a little bit, and weigh it again. You'll see that it weighs more, and that additional weight is the amount of water that is being stored within the pore spaces of the sandstone. But compared to what we call unconsolidated sediments, transmission of water in sandstones is very, very small. And it's almost nothing when you start looking at claystones, again, because those particles are small and flat, and the pore spaces between the particles, the spaces between the particles are much, much smaller. And it's pretty well zero in igneous rocks, which are all crystalline and have no pore spaces, unless they're fractured. So fractured rocks can transmit water quite quickly, but if there are no fractures in an igneous rock, then the water won't transmit at all. The word we give to whether or not a sedimentary layer or a bedrock layer can transmit water is if it does transmit water quite well, we call that an aquifer. And if it doesn't transmit water or transmits water only very, very slowly, we call that an aquiclude. This diagram here shows a common relationship. Yeah, it's a stylized diagram, but nonetheless, it's a relationship showing you, it's a diagram showing you the relationship between aquifers and aquicludes, and how you can have a confined aquifer, which is an aquifer which transmits water, with an aquiclude on top of it. So it's being confined. And so water will move down that aquifer and move downwards towards the ocean, but it won't move down through the aquiclude. But as it moves down through the aquifer, it will be under pressure because it will want to sort of get more and more water. It will want to move in all directions, but it can only move in one direction. And so pressure will build up in certain parts of the aquifer. If you stick a pipe down through that aquiclude into that confined aquifer, you'll get water coming up as the pressure is released. And we call that artesian water. And artesian water is particularly important in Australia. You may have heard of the Great Artesian Basin. Well, here is the Great Artesian Basin, and it is a huge, huge resource of water. Far greater than the good old Sydney Harbour, people seem to refer to, and God knows how many Olympic-sized swimming pools there are in the Great Artesian Basin. You could probably work it out. But it is massive. And this artesian water is a supply in those arid regions of water for stock and domestic uses, and was commonly accessed by banging down a spear point and just releasing that water and allowing the water to run out. One of the really cool things is
If the confining layer is fractured, you can get water coming up naturally.
Natural springs. You have this ecosystem forming, and it is an incredibly unique ecosystem. It's called a mound spring. And as the water comes up, brings up tiny amounts of sediment that gets deposited, and over thousands and thousands of years, a mound develops with this fresh water bubbling up slowly from the Great Artesian Basin. And in those little ecosystems, which in the desert, surrounded by desert, can be these incredibly unique animals and plants, including some fish living in those mound springs, nowhere else in the middle of the desert. The last thing we'll look at is that process that returns all this water back into water vapor that can go back up into the atmosphere and form clouds again, and that's evaporation. So evaporation is simply the transformation of liquid water back into water vapor, and that's driven by the sun. But looking at it more closely, it's not just water from what we call free water surfaces like oceans and lakes, but transpiration as well. So from trees, we should know probably that trees transpire water through their leaves. And you put those two things together and we call that evapotranspiration. Now we can look at evapotranspiration. Let's have a look at it in Australia. This is a map of what we call potential evapotranspiration. This is the maximum amount of water that could be evaporated if there was unlimited amount of water in different parts of the country. Now we use this piece of equipment to measure evaporation. It's called a pan evaporation. And very simple, you fill it up with water, leave it out for a day, and you measure the fall of water. We get the transpiration side, the potential transpiration, by applying what's known as a crop coefficient. And so we multiply that out and we get the estimated potential evapotranspiration. Potential because it's the maximum amount that would occur if the supply of water was unlimited. And if you have a look at the map again, you can see that in the hottest, driest parts of the country, that is where you get the maximum amount of potential evapotranspiration. If, however, you look at the actual evapotranspiration, you get quite a different map. And so this map here, again from the Bureau of Meteorology, shows you the actual evapotranspiration in different parts of the country. And again, if you look at that very, very dry, hot area, about there, you can see, compared to what it was, it's much, much lower. And that makes sense because it's the actual amount of evapotranspiration. So it depends on the annual rainfall that's there. And so you can see the relationship across the country. Now, one of the more useful things you can assess by knowing something about the potential evapotranspiration and, say, rainfall, is that you can work out whether or not you will get an excess amount of moisture in that landscape. Because if the potential evapotranspiration is higher than the rainfall, then all of that rainfall will disappear up as evapotranspiration. It's only where you get areas where you get a higher rainfall than the potential evapotranspiration that you start to get moisture collecting. And again, it makes sense. Where are those biggest surpluses? Well, they're in the tropical regions. Well, what grows there? Lots and lots of tropical plants. And where do you get the greatest deficits? Well, you get them in the arid regions. What grows there? Not very much, just highly adapted plants, highly adapted to those very dry areas. The last thing we'll talk about is the modification of the hydrological cycle. Now, we talked a little bit about the modification using artesian water and putting down wells and extracting water that way. But I guess the main way we affect the hydrological cycle as humans is via the modification of waterways.
I just thought I'd better jump in here Of course, what I meant to say was the main way we modify the hydrological cycle is via climate change, which we'll talk about in another lecture. I just got a bit carried away with river systems. Okay, back to this one.
Now this diagram here is of the Murray Basin, and it shows all of the locks and weirs and dams that have been placed on the Murray system, right from the Snowy Scheme up in the mountains, right down through the main weirs and dams like Hume Dam and Dartmouth, all the way down to all the locks and smaller weirs that provide a pondage so that water can be extracted. So that's one way of modifying it, but that system has modified the system even more. And if you look at this diagram here, this is the discharge of the Murray system over an average year. And you can, in what we would term normal conditions or natural conditions. So this is a model of what the river flow would have been like before humans came along, or certain humans came along, and started to modify the system with dams and weirs. And the relationship makes sense. You get higher flows in that spring period, which reflects higher rainfall in the southern part of the continent. And then as the climate dries out over summer, then the flow of the river falls down and you get much lower flows over summer. And that was the case before we put dams in, because that natural flow was a bit problematic for us living in the southern part of the country, because we like to grow things over summer. Crops grow more and pastures grow more over summer because it's warmer. The problem we've got is that there's not a lot of rainfall. So we put in these dams to help us to provide water to irrigate those crops and horticulture crops and some pastures over the summer months. We also like to swim in the river. If you live around where I do, swimming in the river is a big thing over summer. And if you have a piddling little creek over summer under natural conditions, then you probably wouldn't like to swim in it. So the system of dams that we have on the Murray system also provide for significant recreational activities, which, you know, we're humans and we like to do. But all of that together has produced a change in the flow, which looks more like this. And putting the two graphs together, you can see a significant change in the flow, in the discharge over a year, comparing the natural system to our modern day system. And that, of course, has had significant problems, or had significant effects on the natural ecosystems, in particular the flooding regimes, so the floodplains, the river red gum forests, which are adapted to floods at certain times of year. The dams do two things. They stop the floods, because we don't like floods because they're a bit damaging, and they are. All right. So if you live around here, you don't want to have huge floods, so dams stop those. But they also change the high flows, which might fill some of those wetlands and some of the floodplains. They change that to a different time of year. And many aquatic species are also adapted to high flows in that spring period and low flows in the summer, whereas our introduced species, such as carp, are adapted to more of the European flow systems, which are more of a natural, even flow throughout the year. And so the flow systems that we've put in are favouring the introduced species and not favouring and causing problems with the natural, with the endemic species. So that's just a way that we've modified the hydrological cycle for some benefit, but of course, as always, there's some downside which we somehow need to manage so that we can try and get the best of both worlds, which sometimes works and sometimes doesn't. Okay, so that's the end of the hydrological cycle.